turbulence in superfluid helium-4 and superfluid helium-3, for example, by applying some kind of thermal disturbances. Typically, you put in some electrical resistor and apply very small heat, a very small voltage, and you dissipate actually some energy into the fluid and will create a mass very easily. Mechanical stirring is also very simple. So you can use grids or forks or propellers, big and small. You can use ultrasound. Vortex rings have been used. And atomic BECs can be turned into turbulence. Similarly, for example, you can use a laser as a stirrer rather than a propeller. Or you can simply move about your trap, which confines the atomic condensate, shake it. You can phase imprint vortices. You can also do a quick thermal quench, cool the system quickly, and you will left with phase defects, and therefore vortices. So here is a kind of gallery of devices. So you see on the left, for example, a box. This box contains, was about 10 centimeters big. It contains a liquid helium with 2 counter-rotating propellers producing some kind of turbulent carbon flow. And a much bigger version of that exists now in Grenoble. This is almost 1 meter wide. So it has the cooling power required to operate it are immense. Or you can make a proper wind tunnel like engineers of NASA and Boeing and Airbus. So you push the liquid helium to a pipe and make it to go fast. And you control it in the usual ways you do with wind tunnels with various kind of initial grids. So you see the scale of the device here. The scale of that apparatus is also very big. This is a human being. Small devices, for example, are vibrating forks. This is the vibrating fork, which is inside this kind of object. Or small vibrating wires or grids or meshes have been used. So at the top what you see is the drawing from a paper in which turbulence was created by a superconducting sphere, very tiny, which was oscillating between 2 plates. And the top left, the standard thermal counterflow. So there is a channel, there is a heater injecting essentially energy, producing normal fluid moving in one direction, and by counterflow, superfluid in the other direction. So another example is a grid which is moved suddenly in fluid at rest. So it's similar to a wind tunnel. Ultrasound generation, if you want to create turbulence away from the boundaries, you focus ultrasound to the center. A neat way to create turbulence is to inject vortex rings, which you can do by essentially applying very high voltage to liquid helium. That will produce an electron which carves a 0-point motion bubble, which you can move about in vortex rings. In condensate, you can shake the trap as in that experiment. So that is how a laser spoon has been described schematically by the authors of that paper in Paris. There is a suggestion here of a double rotation, rotation about 2 axes. That works in if you do it in water. It has been done in Kyoto, I think, and represents the thermal quench. So you go through the phase transition. The order parameter cannot adjust simultaneously everywhere. You're left with domains operating by vortices, which will interact, creating turbulence, which eventually will decay. So there are many ways to create turbulence. The question is, has this to do with the turbulence which we notice in everyday fluid, in water, air, etc., or not? Is it different? So that's a good question. So let me tell you in three words, something about classical, ordinary turbulence. So what is classical turbulence? I would like to stress my point of view here. Turbulence is a problem of physics. It should not be left to engineers. It's a problem of nonlinear statistical physics, where you see an immense number of degrees of freedom which are excited simultaneously. They interact nonlinearly, essentially representing motion of a huge number of length scales. So suppose you face like a volcano, like Mount St. Helens, and there is a pyroclastic flow coming towards you. Don't run away, just admire it. You see some kind of motions on a scale of almost a kilometer, essentially big vortices on that scale, which below away vortices which are smaller and smaller and smaller down to the scale of a millimeter. So it's just amazing. Now that there are vortices in the turbulence, would notice long time ago. So I'm not going to tell you the history of turbulence because I don't know it. I just remarked that perhaps there is some agreement that the first person who noticed that turbulence contains vortices was a painter, somebody who professionally was accustomed to observe very critically and very well. So this is a drawing of Leonardo in the late 1400s or early 1500s, in which he sketched the what happens if there is a jet of water, some kind of small jet of water into a pond. So he represented the disorder essentially by eddies. So the next step in this history is a jump of 3-4 centuries. So we go to Manchester in the late 1800s, Osborne Reynolds, famous for the Reynolds number, and his experiment, which was a long pipe, glass pipe. So he pushed flow along the pipe, and he visualized the flow using some ink. So you see here the injection of ink. When the velocity of the flow through the pipe, of the water through the pipe, was relatively small, he noticed that the ink would remain laminar, but exceeding a critical velocity, it would actually destabilize and fill the pipe with ink. Then he had a very bright idea. He switched off the lights, and he used some electrical spark to see what was going on just for a brief instant. And he saw this kind of picture, which he sketched, so you see lots of eddies. So there are indeed vortices in the turbulence. Now, the other point I want to make is that turbulence is not the same as chaos. Chaos is defined technically as essentially some kind of disorder of a finite dimensional system. So very limited number of degrees of freedom. The system must be nonlinear, and chaos is simply the fact that trajectories in phase space diverge exponentially with some positive Lyapunov exponent. And you see an example of chaos produced by a saddle point, essentially, which is easy to create using 4 vortices. So if you have some kind of tracer of the fluid, which can be a particle of dust or something else, if you have 2 such tracers, they will actually be stretched away and diverge in the region near the saddle. So situations like that, of course, are quite common if you have many vortices. They occur more or less everywhere. So turbulence contains chaos, but it is more. So what is that more? So let's go back to Reynolds. He's well known for his first studies of turbulence and his famous Reynolds number. What is it? Well, fortunately, when we study turbulence for typical systems we're interested, like air and water, we can rely on some equations which are known well. Essentially the Navier-Stokes equation written there for an incompressible fluid, so small Mach numbers. So imagine you're interested in some fancy modern car, some moving along the motorway at speed u, the size of the car is d. So the solution which you can get depends, the flow pattern depends on this combination discovered by Reynolds, the scale of the velocity times the scale of the car divided by the kinematic viscosity of the fluid, which is the viscosity divided by the density. And you see immediately from this equation that this number actually somewhat describes the ratio of the magnitudes as estimates between the inertial term, the quadratic nonlinearity of the Navier-Stokes equation, and the viscous term. So it's the ratio of forces essentially acting on fluid particles. So the next step in the history of turbulence can be taken as 1941. So that is the date associated to the work of a famous Russian mathematician, Kolmogorov, who described turbulence in the simplest possible forms when it is actually homogeneous and isotropic, away from boundaries, in some kind of statistical steady state. That means essentially that turbulence is forced, otherwise the energy would decay because of the viscosity. So we keep forcing it until it settles down to some mean value with fluctuations. And in this idealized form, a good question to ask is, what is the distribution of the kinetic energy over the length scales? So we must think of the length scales as, for example, represented by the wave number k, which would be the magnitude of the wave vector you use for Fourier transforming your field. And you can represent the total kinetic energy of the turbulence in this fashion. So that would be equal to V squared. That's the energy per mass. You represent it essentially over Fermi shells with this spectral density. And the result of this approach is that this distribution has some particular scaling. It's this famous 5-third law of Kolmogorov. So that's presented here on a log-log graph. So most of the energy is contained in the very large length scales, which means small wave number k, the size of the system, described by the capital letter D here. And then the way this result is interpreted is that the energy is transferred by the nonlinear interaction contained in the V dot V term of the Navier-Stokes equation to smaller and smaller length scales, higher and higher k's, until the scales, until the eddies which are created in this fashion are small enough that the viscous forces can actually destroy them. So that is why viscosity actually plays the role. So we have a range of wave numbers, a range of length scales from this kd to this k eta, let's call it eta, the dissipation length scale, in which energy is simply shifted. So energy comes into the system here and exits there, becoming heat. So this is the famous Kolmogorov-Richardson cascade associated with this law. And you can see that if you look at the ratio between the large length scale and the small length scale, it's given by this number, and you see the Reynolds number appearing. So eta divided by capital D. So the Reynolds number can be interpreted for this homogeneous isotropic turbulence as a measure of the numbers of degrees of freedom which you have in your system in one linear direction. But of course, there is more than that. There are other features of turbulence which go beyond the 1941 of Kolmogorov. For example, essentially some correlation functions which you can define in this fashion, as written there, deviate from this simple scenario. Experiments don't agree with this scenario. K41 will be the theory, and you see experimental data deflecting. There are also other issues, such as the turbulence is not really some kind of simple homogeneous disorder. Observations and numerical calculations since the 90s show that it contains regions of extreme concentrated vorticity, called by people, some people call them worms. They look like worms. They are metastable, they appear, disappear. So there are all sorts of phenomena. So the question is, does the turbulence in our superfluids or Bose-Einstein condensers has to do with this? So people have looked at various systems. Historically, the most studied is this case, the case of the counterflow, turbulence generated in liquid helium by a heat flux. And this is important because more is known about this problem, although actually it's not very clear. There are still many open questions. And it is important in the engineering applications. Helium is used to cool substances or devices, and keep them at temperatures around 1 degree. So it is important. So typically what you see is that if the heat flux which you apply is small enough, you have this perfect heat conduction, which breaks down, however, if you try to push the counterflow to very large values. So when this counterflow is very large, the ideal heat conduction breaks down, and you have lots of vortices. And vortices are always energy losses, because this motion around the edges or around the vortex lines means that you're supplying energy for going nowhere. You're just erratically moving. Well, actually, I said this problem is not that understood, although it is historically the first quantum turbulence created in the lab, because there are actually various regimes which are not clear. So let me put on this diagram the density of vortices defined as the vortex length per unit volume, which is observed. Various techniques exist in helium to measure this directly, which do not exist, unfortunately, for bosons and condensates. So, and we are plotting results versus the heat flux, which is a measure of the counterflow. The two quantities are proportional. So if the heat flux is actually small, until you reach this value, QC1, the first critical value, you have the perfect heat conduction, which makes helium a superconductor. Then you get a regime in which you create superfluid vortices. But it is thought that the normal fluid, which moves in the opposite direction, remains still laminar. And then there is clearly a break in the experimental curves. So there is more disorder, clearly. And so the idea is that, common idea is that the normal fluid itself becomes turbulent. So we have turbulence of two fluids which are coupled together. So we have two turbulences together. This is quite strange. But there are, of course, physical systems which do that. If you take the interior of the sun, you have a field which is turbulent, which is the velocity field. And there is also a magnetic field, which is not a fluid, but looks like it's a vector field anyhow, which is also turbulent. So, and the two fields obey very similar equations. They are coupled nonlinearly. So it's a really difficult problem. So possibly this is the kind of problem we face in this regime. And at the moment, experimentalists can study this transition. So perhaps this is true. This diagram, perhaps it is exactly as I'm describing in a qualitative way. So it is still somewhat an open question, which we need to answer. So let's move to other forms of turbulence. For example, created by counter-rotating propellers, the von Karman flow. So you see at the left the first experiment of this kind done in this configuration, and you see energy vector measured at various temperatures, and you see that the scaling of Kolmogorov -5/3 appears very well. So it's important here to notice that the first line, the line A, is taken at temperatures above the lambda point where liquid helium is just a cold liquid. Very low viscosity, but a classical fluid. So 530 is expected. What is not expected is actually that it is the same law at lower temperatures, down to temperatures of the order of 1.4 Kelvin, where I think only 4% of the liquid helium is thermal. This version of the experiment has been repeated many times. So here I have data for superfluid wind tunnel called 2P, which exists in Grenoble, and you see it beautifully, this classical 5/3 law. Okay? Now I must stress that this regime extends from clearly some large length scales to small length scales, which in this case have to do with the vortex separation. That's the quantity which I denote with small l here, the average distance between vortices. And the reason is that if you go to scales which are smaller than that, essentially you're looking at what happens in between individual vortices. So you lose the idea, the possible connection with the hydrodynamic, the classical hydrodynamics. That's why some people like to talk of classical length scales and quantum length scales. Looks like a fancy name, but that is what it means simply. Now, of course, there have been theories, and mainly numerical calculations, of this problem, starting from this paper, which was actually the first, it was a study done more or less at the same time of the first for Counterflow experiment. So the calculation is a decaying state of turbulence starting from some large-scale flow, which was chosen to be some Taylor-Green flow, having this shape from the point of view of vortices, which decays. And during the decay, the interaction of the eddies, represented by many vortices, created this regime, which is the Kolmogorov regime. So I have similar pictures. That was done using the Grosspitesque equation, by the way, and you should expect the same result with other models available. The other important model available is the so-called vortex filament model, or the Biot-Savart law. I'm going to describe models at the last lecture. Today, I'll concentrate on results. So the two models agree. These are not particularly convincing, but they were the first. Okay? So they were, I think these two papers are remarkable. So you see the spectra which are consistent with the Kolmogorov law, using both models consistently with experiments, and everybody then essentially followed this. So you see an example here. This is a calculation in which the experiment of Wolfsme and Golov in Manchester was simulated by injecting vortex rings. So the turbulence which you see here, a tangle of vortices, has this kind of spectrum. So you see the Kolmogorov law that in the right, in the expected range of wave numbers from the large scale of the system, with the box size with periodic boundary conditions, to essentially this k wave number corresponding to the distance between vortices. And then, if you go to shorter scale, in the vortex filament method, you just see individual vortices, and you're actually look at them very closely. So what you see is essentially the spectrum of a single vortex, which is this decay k to minus 1, which you can recover by hand. Now, the Kolmogorov spectrum, as I said, can be obtained using the Grosspitesque model, and there is this idea of producing it in a condensate by rotating the trap about 2 axes. So this is not now a periodic system, it is actually a confined system. And essentially, it is what people could perhaps try to do in experiments with atomic condensates. And again, because of the large-scale forcing, the rotation of the entire system, you see the Kolmogorov spectrum appearing in blue, the blue line with the right slope, in the correct expected range of wave numbers. The line is simply the compensated spectrum, so the spectrum has been multiplied times k to the plus 5/3. So the fact that the line is almost horizontal proves the point. So the question then is, but what is the origin of the Kolmogorov spectrum? After all, you can get it simply from some very simple dimensional scaling of the Navier-Stokes equation. Where does it come about in our systems where the vortices are quantized? This is not simple to answer, particularly when you are in the presence of two fluids, like liquid helium at temperatures above 1 Kelvin. There are two interacting fluids. So let's consider, for simplicity, just a case of very low temperatures, the limit of T going to 0. So you see a very dense vortex tangle computed by Andrew Bagley in a periodic box. It's so dense that everything is dark because there are only vortices. So the question is, what is the nature of the flow which is there? Clearly, it's very complicated looking. And the spectrum, the energy spectrum, which can be computed, is indeed a rather good 5 law, as you can see at the top right. It's the black line, consistent with the Kolmogorov theory. In the right, in the expected range of wave numbers. So to understand what's going on, it's useful to try to define some kind of vorticity. In this model, we have only vortex lines. So essentially, there is potential flow around singularities. So what is the vorticity? Well, it's delta functions. But we can try to give it a meaning in a continuous fashion in various ways. For example, here, the idea was to create some kind of Gaussian kernels around these vortex filaments and try to integrate and create a continuous field. And an example of this representation is given here. You see here two vortex lines which are anti-parallel, and they're wiggling. So being anti-parallel essentially produces a cancellation of the velocity field. So essentially, there is not a great energy there. There is not much velocity field, and so there is not much vorticity. And indeed, the reason actually there are tiny wiggles is simply to justify the fact that we can produce something which is weak on this scale. So this very pale color simply means very weak vorticity caused by the wiggles. Otherwise, there's a perfect cancellation. On the contrary, if the vortices are parallel, then the flow adds up. So we have actually two quanta there. So we have some vorticity, and in a coarse-grained sense, we have some kind of tube with some strong vorticity, which you see represented there. So if you proceed in this way and take the spectrum, then you recover, indeed, a spectrum for the vorticity, which is the bottom curve, which is consistent. It's not very good looking, but it is consistent with the slope of these blue dots, which is the expected vorticity spectrum from the Kolmogorov theory. So indeed, we have actually classical turbulence here, hidden in between these vortices. So why the 5/3 slope? Well, the origin of this scaling is the presence in the turbulence of vortex lines which have come together in a parallel fashion. Now, this is actually something which vortex lines would not necessarily like to do, because conservation of energy would actually make vortex lines to turn and become antiparallel. So it's something which you can only create for a while and in a small region, and it should not stay there for too long. So it's this polarization of the vortex tangle which is responsible for the Kolmogorov law. And you see here a justification. So here the vortex lines are color-coded, yellow and red, depending on the coarse-grained vorticity. So when they're yellow, there is large vorticity, coarse-grained vorticity. So it means they are parallel. When you see red, they are not parallel. They are at random with each other. So here you see the decomposition. This tangle of vortices has been decomposed into two parts, essentially the parallel and the random part. And the energy spectra have been computed for the total, for the true combination of the vortex lines, and for this decomposition, which is somewhat arbitrary, because one has to choose some kind of vorticity level corresponding to where you put the threshold. But this is not, where you put exactly the threshold is not important, because in any case, you get the same trend. So the entire turbulence obeys the Kolmogorov spectrum, and this part, which is the random part, does not. Has a spectrum which is actually quite different looking. So it's the parallel lines which construct the turbulence. Indeed, you see that if you put a bundle of vortex lines parallel to each other, you create a large-scale flow. Velocity field adds up. So this large-scale flow actually has lots of energy, which goes, essentially explains why the left part of the spectrum is much larger on the logarithmic scale. So you get large energy-containing eddies, or bundles. Vice versa, the vortices are random to each other. In one dimension, put vortex lines up and down. The velocity field cancel out almost precisely, and there is not much energy there. But there are other properties of the turbulence which are worth looking. For example, a very simple one is the velocity components. Are they small? Are they large? So one can simply measure them and construct a PDF, a probability density function, essentially a normalized histogram. So take the x velocity components, measure it thousands of times, and make a histogram. So what does it look like? Well, it has been known for many years that in orderly homogeneous isotropic turbulence, this kind of histogram is Gaussian. So you see experiments and also numerics give nice Gaussians of this histogram. Yes. Well, I think it's, yes. Okay. He was part of the experiment. Now, when this was measured in superfluid helium, there was a surprise. So the measurement was done by using tracer particles, small solid hydrogen tracers about the size, about 1 micron in size. And they did not find the Gaussians. They found power laws. So notice here the curves. So they could only measure velocity components in 2 directions, not 3. We have the black and the red curve. And the Gaussian fit to the data would be the blue line, which is underneath. So definitely it's not a Gaussian. It's a power law behavior. It scales like essentially the velocity to the power -3. So what's the difference between Gaussian and power law? Well, the difference really is in the high velocity, in the extreme event, you want high velocity, high positive velocity or high negative velocity. If the statistics are Gaussian, they are very rare. If they are power laws, they happen a lot. So essentially, there are lots of events with high velocities. So which kind of events? High velocity. Well, more measurements of this kind were done by other labs. You see here the trajectories of tracer particles. You see, again, these statistics in counterflow turbulence, and also numerics. And again, you see, so this was done by measuring the velocity in a computed turbulent condensate. You see again these power laws in 3-dimensional turbulence, essentially the turbulence corresponding to this system. So we have non-Gaussian power laws, but also in 2 dimensions, and also with very simple vortex points method, you get power laws. So what's the reason? Well, the reason is, I think, is the following. If you have a single vortex, it's easy to think that around the vortex, because of one vortex will induce essentially power law behavior. Because the velocity field goes like 1/r around one vortex. Now, why should do power laws if you have many vortices rather than Gaussian? Actually, it's more subtle. But the answer contained in some papers by Tony Leonard and students in the 90s, in the early 90s, when vortex methods were somewhat popular. That was before parallel computing. So people thought that vortex methods would be useful for computing high-intensity turbulence. So they thought a lot about that, and they showed that if the vorticity is concentrated, then the approach to Gaussian, which would happen with the central theorem, limit theorem, does not really happen. It's extremely slow. So you never see actually Gaussian. You only see power laws. In other words, the power laws are the manifestation of the very concentrated nature of the quantum vorticity. We have vortex lines and we induce power laws. So even when there are many. So now this paper does not make any, this paper and some other papers written at the time don't make a reference to superfluid helium. They're just papers of numerical analysis, but I think they contain the physical answer. Okay? Now there is another interesting point. When one does an experiment, one does not measure the velocity at a point in space, like in a numerical calculation. One measures the velocity of the tracer. So there is a region of measurement, which in the original papers by Pauletti and Dan Lathrop and Srinivasan in Maryland, essentially is the size of the micron, which is the size of the tracer. Now, you can actually repeat the calculations and consider what happens if the region in which you compute the velocity and take an average value is small or big compared to the typical vortex distance. So essentially, are you measuring the velocity at the point, or your volume is large enough to include many vortex lines? Because if the region of measurements is small, then you get the power loss. You see the singular nature of these quantum vortices. But if it is actually a rather large region of measurements, because the turbulence is very intense and the lines are very close to each other, then you recover Gaussian. And that is actually what we found by doing this numerical exercise. And it was also found in Prague by doing experiments. It was really the same thing. Rather than an average over space, they did an average over time of the tracer particles. So you see a transition from power law to Gaussian or vice versa, depending on actually which length scales you're actually considering. So the idea that there is a distinction between classical length scales and quantum length scales actually is correct. So in any case, the velocity statistics give the same information as the spectra, the energy spectra. So we can create regimes at finite temperature in liquid helium or at zero temperature, and also in Bose-Einstein condensates according to the numerical simulations, not the experiments. Experiments are not at this point, in which we create quasi-classical turbulence. Okay? Now, there is, however, something to add. If the temperature of the liquid helium or the temperature of the condensate is very small compared to the critical temperature, the friction is very small. So the Kelvin waves, which are in general generated by the vortex interaction, and they're also particularly generated by vortex connections, will not be dissipated. And in fact, that has been known for some time. It was first Boris Fistunov in 1995 who started thinking really deeply about any difference between turbulence at zero temperature or sufficiently low temperature and higher temperature. So he realized Kelvin waves would play a key role. And in this calculation by Tsubota, which followed, actually, this is very visible. So this is a vortex tangle more or less with the same intensity. At finite temperature, you see lines are very smooth. And at zero temperature, you see that the lines are quite wiggly. That's lots of Kelvin waves. In fact, they are fractal. Okay? If you measure the fractal dimension using standard techniques, you find it is not 1. And so then Svistunov thought of a possible way of explaining some experiments about the decay of turbulence below 1 Kelvin as a process of Kelvin waves which interact with each other, generate shorter Kelvin waves, which generate even shorter Kelvin waves. So a Kelvin wave cascade rather than a Kolmogorov eddy cascade, until the wave numbers, the length scales, would be so short, very large wave numbers, very short length scales, that the motion of the vortices radiates very efficiently sound. You require very short length scales for this to happen. So that was the idea of the Kelvin cascade, and he made predictions about this process. And just to illustrate that the cascade can be triggered by reconnections, I show one of the early papers on this problem, 2001. So you see 4 reconnecting vortex rings. So here they are. The cube is there for visualization only. You see 4 rings which are launched against each other just before touching, and here they reconnect, and you see all the Kelvin waves which are launched, and they are not dissipated by the friction. And you see actually the spectrum which forms. Now, this spectrum actually, the nature of the spectrum, the shape, and the kind of process which generates the spectrum was controversial. For some years, there was an argument between competing theories, one due to Svistunov and Kozik, one due to Nazarenko and Lvov, and the issue was settled by numerics, unfortunately. There is not an experiment which shows this clearly. Nobody knows how to do it, but the numerics eventually became better and better, and at some point, George Krustulovic was able actually to tell that this prediction and the kind of wave interaction which gives origin to the right slope of the spectrum was correct. Okay? Now, there was another interesting prediction there, that there would be some kind of bottleneck between the Kolmogorov cascade and the Kelvin cascade. So what is a bottleneck? Imagine, essentially, it's a probing of impedance matching in the language of engineers. Energy flows down from the cascade of eddies and must continue here into the cascade of Kelvin waves along individual lines until, at extremely small length scales, it's radiated as phonons. So, but here there is this mismatch, and so a possible pile-up. Now, unfortunately, as I said, there is no experiment which clearly shows anything here. But this pile-up clearly is visible in these more recent calculations. This one, for example, also that as a flat region, so a plateau which is forming. But nobody knows more of this problem, because the next step would be to do an experiment. Okay. Now, this is not all that we know about quantum turbulence, because there is another form of turbulence which has been observed, and slowly somewhat acquired a name, and people realize that it's the same in different situations. So I shall call it Vinen turbulence, following perhaps the person who got this point first, who was Grisha Volovic in Helsinki, and he used this name. Now, at the moment, the evidence for the second form of turbulence is somewhat the following. So we have experiments with vortex rings done at very low temperatures in liquid helium in Manchester. We have experiments done with helium-3 in Lancaster. We have numerical simulations of the experiments which reproduce the Kolmogorov turbulence and also the Vinen turbulence. So Kolmogorov turbulence means classical like ordinary fluids. Vinen is not classical. Simulations of turbulence generated by small heat flux. Simulations of the thermal quench of a Bose gas. Simulation of turbulence in small atomic Bose-Einstein condensates. Okay? And more recently, even simulations of dark matter. Okay? So those will be axions obeying some kind of self-gravitating Gross-Pitesky equation. And because of the way the turbulence is created, essentially there is, because of the lack of forcing at larger length scales, which is a major ingredient, the turbulence acquires a different nature. But in the case of condensate, possibly it's not only the lack of forcing, it's also the fact that the system size does not allow that to happen because of the available K space. So what is this turbulence? So first of all, the energy spectrum. We see a typical classical spectrum, Kolmogorov spectrum at the left with the K minus 503 law. So leaving aside the precise slope of the spectrum, notice one feature, that most of the energy is at the smallest wave numbers, at the largest length scales. So it's in the largest possible eddies. Now that is not the case for the Vinen turbulence, which has a spectrum represented on the right with the red line. The energy spectrum seems to peak at mesoscales, typically of the order of the distance between vortices. Then other signatures for this Vinen turbulence are the different way in which it decays, which can be measured. So the vortex length decays slower than in the case of Kolmogorov turbulence. The power is T to the minus 1 rather than minus 1.5. And the energy also decays like T to minus 1 rather than minus 2. If you look at the velocity correlation function, you also notice that the Vinen turbulence actually is very little correlated. If you move away from one position, essentially the correlation drops. So how do we interpret this turbulence? Therefore, essentially some kind of random flow. The vortices don't like to be parallel to each other. They're random. Okay? So it's a turbulence without a cascade. That's how we try to put it. Now this is the original picture of Volovic, who thought of this first. So he made a sketch. So that is how he represented the quasi-classical or Kolmogorov turbulence. He just drew some bundles. And that is how he represented the Vinen turbulence, which some people called ultra-quantum. That's a very strange name, but some people use that. Why? I think they had in mind, this is not turbulence, it's quantum turbulence, but it's not the quantum turbulence we've just learned, it's another. So what is past quantum? Quantum square, or I don't know, super quantum, ultra quantum. So better use the names. So these are cartoons, but actually, if you look at these two vortex tangles computed by Andrew Bagley, you see that the cartoons actually are very, very realistic. This is what is actually plotted here, the vortex lines, and they're being color-coded according to the helicity of the central line, or better. Instantaneous central line helicity. Helicity in a superfluid is a delicate topic. Some people don't know how to define it. Some people know how to define it, or think they know how to define it. Actually, I have my own views, and they agree with some in the audience. Some people like to define it so as that it is zero and then remains zero, which is not very useful, but perhaps it is so. I think that it can be defined in a proper way, making connection with classical helicity. The classical helicity definition is that, omega dot V. So you see why the name was invented. It was invented by somebody who knew Latin. It's a nice name. But what we computed here is actually this expression. And it's easy to show that in the case of vortex lines, the helicity computed exactly according to the definition represents the non-local nature of the velocity at the point along the vortex line. So it represents how strong a line, an element of a vortex line, is moved by other vortices. So in the case of Kolmogorov turbulence, we have bundles. Helicity is large, although on the average may be zero. But in the case of Vinen turbulence, it's very small because the vortices are random to each other. So the cartoon actually becomes very real. And we have this Vinen turbulence. And you can actually work out, we can actually here, okay, you can work out how it should decay, for example. So if you take a vortex line, you have a velocity field which is kappa, the quantum of circulation, divided by 2 pi r. You can think of the energy of a length of vortex line. It's easy to compute it. So you can compute the energy per unit length, which is this expression. You see it contains the square of the quantum of circulation. And in the case of Vinen turbulence, you can actually find the kinetic energy of your turbulence, the energy per mass, which we want, simply as energy per length times length per volume times volume per mass. And so we end up with this quantity. And assuming there is the same relation as we have in classical fluid mechanics for the energy dissipation, proportion to some square of, or some average of the coarse grain vorticity, and making also this assumption that we think of the vorticity as the vortex line density times the quantum of circulation, we come up indeed with the correct observed decay law. Okay? So this is an argument first proposed by Joe Vinen. That's possibly why the Vinen turbulence was named after him. And the different scaling for the Kolmogorov turbulence, which is what we see in liquid helium, simply comes from using Kolmogorov and the same definition and looking at the decay. So we imagine that the dissipation changes. So epsilon, the energy dissipation, changes with time, goes like T2 minus 3, and then you can recover a decay for the vortex length and the decay for the energy. Okay? So these are now pictures which I want to show you. This is a thermal quench of a Bose gas. So we start from random phases, uniform occupation numbers. So essentially, there are lots of ghost vortices. The linearities create a vortex tangle, which then decays. So in the transient state. Now, this is the typical Kibble-Zurek quench, which is done in the experiments. And you don't expect Kolmogorov turbulence to take place here, because there is no forcing at large length scales, and in 3 dimensions, the energy cascade will simply move to the left, but there is nothing to move from left to right. So we get the Vinen turbulence. So this energy spectra which peak at the mesoscales and which simply decay. So although the range of wave numbers which is accessible to the numerics is not that large, and it's never going to become large, even if you use very big supercomputers, it's very visible here that there is a factor of 3 orders of magnitude in energy, which is missing at the largest length scale. So everything fits, energy spectrum, decay loss, and also velocity correlations. And the same for turbulence in a small BEC. So there are not many vortices here. We're on the edge where perhaps we go from chaos to turbulence. And indeed, the K-space is so small, it's very difficult to make sense of any slope on that graph. However, we know what we're looking for. We're looking for some particular laws, and actually they are visible on that graph. In the energy spectrum, in the decay of the length, and stress the correlation going very fast to 0, meaning a random flow. And these are similar pictures for the self-gravitating Gross-Pitesky equation. So another point to make here, which we need to make, is actually critical look at length scales which we have in our quantum turbulence systems. So let me call d the size of the system, psi the healing length or the vortex core radius. So it's a small scale. Yep. I'll go back to the picture. So what do you mean? Here? Yeah, here there are things happening. There is in some there is the numerics which start failing. There is some physics, maybe a Kelvin-Wave cascade if the model allows for that, and if it exists. The emission of radiation essentially of sound, all sorts of things happening at a very high K. Oh, the very low, yeah. Well, this means, okay. Now this system actually, one has to be careful about the lowest K available, because you have essentially one size which is longitudinal and also one size which is transversal. So there is a limit of K across and K along. Yeah, so it's not isotropic. So the fact that here there is not the blue line is very low on the left simply means there is not much energy in motions which are as large as the cigar-shaped condensate. Yeah. Yeah, that's right. So on the left, what happens on the left? Now, if you do, yeah, as I said, then the boundaries become important. If you have a periodic box, then everything repeats periodically with your box size. So you will, if you have turbulence, you will get energy spectrum will go to the maximum value to the left, because the largest eddy would be like essentially a big vortex as big as the box. If you do an experiment, however, in real life, you have to be careful, because at that point the nature of the boundaries will matter. If you have this kind of condensate, the boundary is very soft. In fact, it's moved. The vortices within actually agitate the surface, however you define it. Okay, it's a soft surface, clearly. If you have a liquid, so superfluid helium or water, whatever, then you have to think about the boundary conditions, because, for example, in many situations you have effectively some friction acting at the smallest case. Imagine you're looking at the motion of the ocean and large eddies and these gigantic currents in the ocean rubbing against the continents will slow down. That picture simply says there is not much motion, there is not much energy in the large scale. Of course, one can analyze it more carefully. For example, perhaps one can try to pick up essentially the disturbance of the surface, defining this first surface in some fashion. So I think yours is a good point, because the problem which one faces is that there is not a way to measure the velocity field within an atomic condensate to produce the energy spectra which we would like to have to make a correspondence to liquid helium and classical turbulence. So essentially, this is the point at which we are stuck, and there are sort of two ways to proceed. Either new fancy experimental techniques to see more, to visualize better. During the workshop, Gabriele Ferrari from Trento will be here and hopefully will describe how he can see individual vortices as they reconnect. Or another way is to try to explore the properties, not of the energy spectrum, which is what historically we grew up, we learned that it has been useful, but find some other quantities which actually can be more easily measured in experiments with condensates. So. Information. Yeah. Yeah, I agree. But, the question is, I don't know what to do really with that information. Anyhow, we're looking at final point at the length scales. And so L is the vortex distance, and eta would be what is called the Kolmogorov distance in classical fluid dynamics. That is essentially the length scale at which the scale by scale Reynolds number is unity. So the viscous forces are as large as the inertial forces, and the energy goes out of the system. Now, it's interesting to see that in ordinary turbulence, the ratio between essentially the large length scales at which one injects energy, really, and the dissipation length scale is very big. So this was Grant et al. 61 was an experiment. It was one of the first experiments in which the Kolmogorov spectrum was measured by measuring the velocity field in the sea between two islands forming some kind of channel near Vancouver. So very large scale kind of experiment. So huge number, 1 million. If you think that the Kolmogorov scale is the scale of the smallest eddy, it's arbitrary as a definition because vorticity is continuous in water. This is essentially the the number of degrees of freedom in one direction. Okay. Now, if you do the same for helium, well, the ratio between the large length scale of the apparatus and the distance between vortices can be like 100,000. And if you take, for example, Shrek, which is a very big turbine machine, the ratio of the large length scale to the vortex core, which would correspond to the number of degrees of freedom, is even gigantic compared to that. So helium is terrifyingly turbulent. But for condensates, we have these ratios are only 10 or 100 with existing condensates, which are pretty small because understand the problem is losses during the last stage of cooling. Too many atoms are lost. So, does it mean that we cannot see turbulence a la Kolmogorov in condensates? No, I don't think so, because after all, the picture, I show a picture which is, it was a calculated picture by Makoto Tsubota, what is it here, was somewhat realistic in parameters, although quite optimistic. So it's feasible, but one has, to learn how to measure the velocity, detect the velocity, or something which is related to the velocity, which is not trivial. And the two really put together the spectrum. So it could, perhaps it's possible. There is no reason why it shouldn't. In general, however, the atomic BC have this fantastic property, which is not a negative property, it's a positive property. They are turbulent, but very small. If you take any kind of classical fluid and you make it small, your Reynolds number will drop, and you will not create any form of turbulence. In fact, if you do some microfluids, for example, like engineers do, and you want to create, you would like to have turbulence to mix two fluids, then you have to play tricks with chaos, essentially devices which make use of chaotic trajectories to try to mix, because the Reynolds number kill you. You don't get turbulence. What is unusual of condensates is that they are small, but at the same time, they don't have viscosity, or the dissipation represented by a thermal cloud can be reduced. So you can still get, in principle, a Reynolds number which is infinite, not in the sense of the number of degrees of freedom, but in the sense of a dimensionless velocity. Viscosity is 0. So they're ideal if one wants to study a very strange transition, very strange crossover, which has not been taught really, between chaos and turbulence. Okay? And at this point, I think these are the main conclusions. So the fact that there is essentially a wave function, which is complex with a phase, really creates the property of quantum vorticity, vortex lines, more than superfluidity, creates new physics. Now, there are clearly links with classical physics, the classical turbulence, but there are also many, many features which are unprecedented in turbulence or not explored. So the idea of Vinen turbulence, not clear whether it exists in a classical fluid. The distinction between classical and quantum length scales, this double cascade, also features of reconnections, the issue of turbulence versus chaos. So there are all these problems. So it's a nice, nice open subject. So I think I'm finished, and I think you want coffee. So I think the last time that we meet, I'll try simply to describe the models which have been used to produce some of the pictures. And I thank you for listening.